Should I go ahead and start? Let me close these because it's loud. Okay, thanks everyone for coming. I know 7 p.m. talk's not the biggest turnout ever, so thanks for being here, even if it also wasn't the talk you were expecting to see. I'm going to talk about the x86 assembly language, and I'll also pre-apologize. I was on the standby list, so I had to make a presentation, so the presentation's longer than 25 minutes, so we'll get as far as we can, and then if you want the rest of the slides, I'll have my email address and everything afterwards, but we'll get as far as we can in 25 minutes. So who am I? I'm Stephanie. I am an embedded systems engineer at Battelle Memorial Institute, and I'm also an adjunct professor at The Ohio State University's College of Computer Engineering. Briefly, computer architecture. So we're not going to go into much detail of all of this, but at a high level, your computer consists of some standard pieces. You've got your CPU, some memory, there's a bridge that handles the transactions between your CPU and memory, and then some type of I/O bus that lets you talk to peripheral devices. So the CPU contains a few key pieces. It's responsible for processing information. It contains an arithmetic logic unit, does all your math. It contains some registers, so these registers are important. The registers store data, and because they're in the CPU, they're extremely fast. The register size is 1 word, so on a 32-bit architecture, they'd be 32-bit sized. They're generally named rather than addresses, and it also does the control unit. It actually executes the code that you're asking it to do. So registers versus memory. So registers technically serve the same purpose as memory. Their whole purpose is to store data. But memory is moderate access speeds, and because it's not on the CPU, there's a fetch delay between going through that, basically going through the memory controller hub to get things out of memory. It's cheap to produce, so your computers typically have a lot of it. Registers are extremely fast to access because they're inside of the CPU, but the actual cost that goes into producing the registers is extremely expensive, the type of memory they use, so there tends to be very few of them on your system. So your program, data, etc. typically sits in memory, while registers are used to simply process small pieces of your application at any given time. So machine code. Machine code controls the processor on the most detailed level possible. So the machine code is responsible for moving information in and out of memory, which involves moving it in and out of memory to registers internal to the CPU. It controls the system bus. It's going to control your ALU, control unit. Assembly, on the other hand, is a shorthand, more legible version of machine code. So assembly code uses mnemonics to save us from having to memorize machine code. So assembly allows me to say something like sub instead of having to remember the machine code, in this case, hex 83. So writing in pure machine code is fun. It has its uses, but it's really difficult and uncommon. It's much more practical to write in assembly. So an assembler is a tool that will translate from assembly to machine code, and this process is called assembling. A disassembler is then a tool that will translate from machine code back to assembly code, and it's called disassembling. So there's something called the instruction set architecture, so an ISA. So an ISA defines the processor registers that exist for that particular architecture. So we're concentrating specifically on x86. So the x86 ISA would define what registers are available in x86. It would define the size of those registers. It would also define the address and data format. So when I grab something from memory, how many bytes do I grab? What size of data am I fetching? It also defines the machine instructions. So it defines, can I do things like subtract? Can I multiply? Can I add? Basically, what functionality in the machine instructions exist in that assembly language. So it indirectly defines the assembly language. So it's defining what low-level instructions we have and what those instructions do. So an ISA is just one piece of the puzzle. So an ISA is describing what that architecture has to be capable of doing, but a microarchitecture is actually the way that that architecture would be implemented. So I know you can't really read this flowchart, we're not really going to go over it, but this is the microarchitecture of the Intel Core 2 Duo. So this is how Intel specifically chose to implement the ISA for x86 on its Intel Core 2 Duo. And if you get the slides for me, the link in the bottom that you can't read would take you to the source of that if that interests you. So collectively, the instruction set architecture and the microarchitecture define a computer architecture. So there are thousands of instruction set architectures, there are thousands of microarchitectures, and thousands of computer architectures out there. So architectures at a high level are divided into two main categories: a reduced instruction set computing, called a RISC architecture, or complex instruction set computing, called a CISC. So the difference between RISC and CISC are generally a RISC is a very small set of simple instructions. Because it's a set of simple instructions, it's generally cheaper to create. Those processors are going to be cheaper to produce because they're not as functional. It's easier to design, lower power consumption, which also makes them physically smaller. A CISC processor tends to be extremely large and powerful, but with that comes some of the obvious. It's more expensive to create, it's harder to design for, much higher power requirement, and it's physically larger. So an example of one versus the other, so a hypothetical example of multiplying something by 5. So in a CISC architecture, because it's complex, I probably have something like a multiply instruction, and I can simply say multiply by 5. I can achieve the same functionality in a RISC architecture, but it's unlikely that I'll have the multiply instruction. That's actually a fairly complex instruction. So to achieve the same thing, instead of one instruction, I have to chain multiple add instructions together to achieve the same thing. So same functionality, it was just harder to do it in one than the other. So some examples of each. So in the RISC category, you have ARM is the most popular one. That's what's running on most of your phones, Android, iPhones, tablets. MIPS runs on a lot of embedded systems. You'll see it on networking equipment, routers. PowerPC, this was on the original Macs, and I can't remember what version of Mac they switched over to x86, but on the original Macs they were PowerPC. The Xbox and Xbox 360 are PowerPC. CISC, so your complex instructions, x86, that's what we're going to be focusing on, is a very complex instruction set. So all of your consumer computers, so now all of your Macs, your PCs, and the new Xbox One is also x86 architecture. And the Motorola 68K, really early PCs. So our intro, let's actually talk about x86. So the history of x86. So it all started with the Intel 8080 chip, which was an 8-bit processor introduced in 1974. Sorry, I'm going to get water. The next progression from that was the 16-bit processor, the 8086, which was introduced in 1978. So this architecture has been around a really long time. The next one after that was the 8386. It's the 32-bit architecture in 1985. And lastly, the 64-bit version of that was introduced in 2003 or 2004. So it's a very complex architecture. The Intel Software Developers Manual I have linked here is 4,000 pages long, and it doesn't even begin to scratch the surface. If you really start to dig into writing x86, you'll find that there's a lot of things missing from this manual. So even at 4,000 pages, it is missing a lot of information. So today, generally the term x86, if someone says that, they're referring to all of the architectures based off of the original 8086, all the way back to that original 16-bit architecture. And the term x64 typically refers to a 64-bit version of x86. There is a lot of overlap between the 32-bit and 64-bit versions, but specifically for this talk, I'm just going to talk about the 32-bit version, so just x86. All right, so if you recall, the ISA for x86 It defines its functionality and features, but it doesn't technically define how to write it. So it says things like you will have a multiply instruction that can multiply 2 registers, but it doesn't actually tell you how someone would write instructions to do that. So if I'm writing an assembly code, there are 2 main branches of x86 syntax that exist. The 2 branches are AT&T, which is used by GCC's compiler, and Intel, which is used by Intel. And there are hundreds of smaller variations, but for the most part, you're always going to generally run across either AT&T or Intel syntax for x86. So specifically for this talk, I'm going to show you guys how to use the assembler NASM. It's the net-wide assembler. It's extremely popular. It's free. And NASM uses Intel syntax. So we're going to specifically focus on Intel syntax, but I will briefly show you what the difference between the two is in case you come across some AT&T syntax. So almost universally true, but specifically true with NASM, lines do not end in a semicolon. Semicolons are used to start a single comment, a single line comment. So if it's old habit that you end every line with a semicolon, it's not going to cause any harm. It really just means that you're adding a comment at the end of each of your line. So generally you have instruction, semicolon, comment. All right, the registers. So we mentioned these before, but the registers are how the processor stores information. So the processor can access memory, but since the system's memory is not a part of the actual processor, that process is extremely slow to getting things out of memory. Registers are contained in the actual processor, so it's extremely fast to access data and manipulate data that's in them. So it's easiest to think of the registers as 32-bit variables. Each has its own name, and it can be modified, not the name, but the contents. But there are a very limited number of registers, and they must be shared with the whole program, and not just the whole program, but everything that's running on your CPU is sharing the same registers. So when they run out, they need their data stored back to memory. So a typical execution of a machine instruction would be fetching data that instruction needs from memory into the internal CPU registers, do the work on the register, or work on that data, save the data back to memory, repeat. So that picture is kind of blurry, but this is the registers that exist on the x86 CPU. Fortunately, you don't have to memorize all of these because most of them are reserved and only accessible by the CPU. So for writing our machine code, there's a very small subset of them that we are actually going to be using. So there's 2 categories of them, the general purpose registers and the special purpose registers. So the general purpose registers, we have those 6 that we're allowed to access, and the special purpose registers, we have the instruction pointer and the flags register. So all of the registers I mentioned earlier, we're going to focus just on 32-bit. So all of these registers are 32-bit registers. And you know they're 32-bit registers because they all start with the letter E. So anytime you're looking at an x86 register, if it starts with an E, that stands for extended because it was extended off of the original 16-bit architecture. So if a register starts with E, it means the 32-bit version of its 16-bit predecessor. So here's a sort of a different look at all the ways we can access the memory in those registers. Because x86, it's an old language, but Intel works really hard to keep backwards compatibility, so instead of wiping out old functionality, they're constantly just adding on. So going back to its days of being a 16-bit architecture, you can still access all of the 16-bit registers. So of these general purpose registers, if I use the E version of their name, so if I use EAX, I'm accessing the full 32-bit value stored in that register. But I can still access smaller subsets of that register. So if I drop the E and just use AX, I'm actually accessing just the lower 16 bits. I can go even further and do either an AH or an AL for accessing the high 8 bits of the low 16 bits or the low 8 bits of the low 16 bits. And that's only on these main 4 general purpose registers up here. So they classify ESI and EDI is general purpose registers also, but they don't have that fine grained granularity where I can talk to smaller subset versions of them. They can only be fetched in their full 32-bit versions. And then you have the stack pointer and the base pointer, which also cannot be accessed in smaller subsets. But those are not registers that you're generally going to be using for a lot of your data transfers or data manipulations because they serve a specific purpose in the architecture. Your code probably won't work very well if you manipulate those too much. All right, so let's talk about some actual x86 instructions. So there are far more instructions than what I'm showing you here, but a lot of them are very small corner cases of use. As I said, x86 never wants to break backwards compatibility, so they just keep adding to the architecture, and it is essentially a huge behemoth at this point. But these are the useful instructions. And because this talk is short, the ones that are bolded are the only ones we're going to go over specifically. But these are all I would say if you want to learn x86, these are the base set of instructions that you should be familiar with. So how I'm going to write stuff on the next couple of slides. So if anywhere you see that I've written in carets a reg 32, it means that any of the 32-bit registers could be in that location. It gets other bitness granularity, or if you just see reg, it means any of the registers could be used there and any subset version of them. Mem simply means any memory address. Anything built off of the con keyword means a constant, essentially. So what I mean by that, so let's look at the move instruction. So the move instruction in Intel syntax starts with the destination, comma, then the source. And it simply moves data from the source to destination. And here's that syntax. So there's specific combinations of, they're called operands, which I'll get to in another slide, but there's specific combinations of operands that you can use for different instructions. So this essentially just lays out the types of operands, the types of source and destination that you're allowed to pair together. So there are certain restrictions. For example, you can't have two memory addresses. So you'll see I can't move from one memory address to another memory address. If I want that as my end goal, I always have to have an intermediate step where I move out of memory into a register and then move that register into my new memory location. And a specific example is moving from EBX into EAX. So simply copy the contents of EBX into EAX. So the move instruction is a little deceiving that it says move. It's actually a copy. It does not remove the contents from EBX. It's simply copying it over to EAX. So add op1, op2. It simply adds the two operands together and stores the results in the first operand. Here's the combination of operands that you can use, and a simple example of us adding the value 10, so constant value of 10, into register EAX. So I'm specifically using this one. I'm adding a constant to a register. So subtract. It does the same thing. I have two operands. It subtracts the second operand from the first and stores the result in the first operand. I can do it between two registers, so I can subtract the top 8 bits of the lower 16 bits of the A register from the lower 8 bits and store that into AL. I can subtract a constant. So the difference between, I mentioned that we're writing in assembly code so that we can use mnemonics, so I can say sub. So while these both look like sub instructions at the assembly level, at the machine code level, these are actually all encoded differently. So each of these would result in different machine code. That sub instruction is different for each of these combinations, which is one of the advantages of writing in assembly, is that I don't have to memorize the difference between all of these subs. To me, they're just subs. I don't need to know that each one has a different machine code behind it. So the AND operand. It does a bitwise AND of the two operands, and I have the truth table for ANDs over here. And it saves the result back in operand 1. Here's all the different operand combinations that you're allowed to use. You'll notice none of these allow two memory addresses. I don't believe there are any x86 operands that allow you to do two memory addresses as the two operands, so you always have to have that intermediate step. So I can AND, in this case, ANDing it with a constant of 0f in hex. And OR, So if I have an AND, I need to be able to do an OR. So it does a bitwise OR of the two operands and saves the result in operand 1. Here's the various syntax and the same example, but now with an OR. An XOR. So an XOR is an extremely useful operand, and it does a bitwise XOR of the two operands and saves the result in operand 1. So for those not familiar with an exclusive OR, I usually just remember it as long as there's an odd number of 1s, then I get a 1. So if I had 2 1s in this case, then I result in a 0. As long as I only have 2 1s, so if I had a 1 and a 0, you get a 1, a 0 and a 1 results in a 1. So an exclusive OR. An easy way that you'll see often used in x86 to set a register to 0, instead of moving a 0 into a register, it's actually faster to exclusive OR it with itself, which will always set it to 0. So setting a register to 0 is just XORing it with itself. So a NOP. A NOP is very popular in the security world, and it essentially just means no operation. It literally does nothing. It just consumes a clock cycle on your CPU. It compiles to exactly 1 byte of machine code, which is a hex 90. And this is commonly used for, so the legitimate uses are timing, memory alignment, something called a branch delay slot that a lot of RISC architectures have. It's potentially a placeholder to be replaced later, so people who are making code that is designed to be hooked legitimately to add functionality will often leave series of NOPs in there, so that later when you apply patches or send out updates, you can hook those NOPs, overwrite them with your new code to add new functionality. So where they're used in hacking a lot is, so hacking likes to do NOP sleds. So if you've ever done a buffer overflow, you're going to need something called a NOP sled. It's essentially just a series of NOPs. Because NOPs do nothing, the entire goal is that you don't know where your code is jumping. So I'm just going to put an instruction that does nothing, and it'll just keep doing nothing until it reaches my code. So cracking, so knopping out, if there's ever a security section of the code that you simply don't want to run, the easiest way to get rid of it is to just simply nop it out. So just make every instruction a 90, and the CPU will do nothing. Alright, so I mentioned that there were 2 main branches of syntax, so I'm specifically showing you Intel syntax in all of these slides, but I do want you to know that AT&T syntax exists. These are the 2 main rivals. I personally really don't like AT&T syntax, but it is popular. You will run into it from time to time. So the main difference that I want you to know about is that the operands are in the opposite order. So for example, the move, I have a source and destination. They're flopped on AT&T syntax. So if you're ever looking at someone else's code that's written in AT&T, that's usually the biggest hurdle, is understanding that the operands are switched. The other changes, the operands typically contain a size in AT&T, so the equivalent code between AT&T and Intel in this table, you'll see on the left-hand side for Intel, I simply have a move, but I'm not specifically specifying the size, whereas in the AT&T syntax, I'm specifying moving along, so move 32 bits of a 1 into the EAX register. So a majority of their calls will have a size letter at the end, so either a byte, a word, or a long. The other difference is all registers are accessed with a % in front of them in AT&T syntax, and that's the main reason that I don't like typing AT&T. It's just an extra keystroke every single time I want to access a register. Programmers are inherently lazy, so I don't like doing this. And the last one is memory references are done with the parentheses instead of the square brackets. So if you ever come across AT&T syntax, that's the difference between the main 2. Syscalls. So there's something called syscalls that can be made from x86 to achieve some basic I/O functionality. It varies by OS, but specifically for Linux, there's this nice list here, but I'm just going to tell you the main 2. So syswrite. So it's handy to be able to write out to the console from x86. And the way you do this, there's several ways. You could get a little more complex and link with a higher level language like C, or if you want to stay strictly in x86, you can use this syscall as long as you're targeting Linux. With these instructions, and I have 1 minute left, so I'm going to charge through the next couple of slides, and this is how you can write out to the console. So here's an example of writing out. Again, if anyone wants these slides, my email address will be up and I'll send them to you. Sysexit, so this is how you make your application stop. Otherwise your application will probably run until it hits invalid memory and you'll segfault. So if you want to exit your application gracefully, you can call sysexit. So here's how you invoke it. So here's a simple hello world in x86. I'm using that int80, that syscall, to write out the string, and then I'm exiting my application. So really quick, if you get the slides from me, I have instructions on how you build all of this. I have sample code. Again, I was originally targeting an hour presentation. So if this interests you at all, please email me. There's a lot of useful stuff in here you can use to start writing your own things. I've also boilerplate code, how to declare variables, and then how to run everything through GDB. So how you can debug when your x86 code doesn't work. So I'm going to zoom through all of this. But just to dangle the carrot so you guys all want the slides, look at all this useful information you could have. So much useful information. Oh, and I went past my email address. Okay, so that's a 0. So 0xshadowfax@gmail. Email me. I would love to give you the slides. I love talking about x86. This is what I teach at OSU. So email me any questions you have. Sorry we didn't get to the rest of the content, but it's all useful. You should all want the slides. I'm done. We ran out of time, so thanks.